So hey folks, Assalamu alaikum. In this video we're going to learn about linear algebra, vectors, the norms, how to represent them in our coding, basically in Tensorflow, PyTorch and Numpy and so on. Okay, so let's get started with it. So if you are familiar with Python, that's obviously big plus, right? Python, so feel free to learn the basic Python, and obviously linear algebra, matrix, tensors. If you are good with it, that's good. So let's get started. So first of all, assuming that you don't know about these things, we are just basically going to start about something called algebra. So what is algebra? Algebra is basically some sort of arithmetic that includes non-numerical entities like x. So for example, your friend just came to you and asked, okay, just let me know this thing, like there is something in a box which we can multiply with 2 and then add with the multiplication value, we just add 5 and we do get 25. So what will be the value for this box, or what will be the value in the box? So you can just put any sort of alphabetical value, something sort A, B, C, D, X, Y, Z, whatever it is, which is not numerical, because we are trying to find the numerical value. So you can just do that. That is basically a linear equation. Okay, linear equation. Now we can say Y, Z linear equations. Like it can be 2 or X, whatever it is. That is not a big problem. So if it was, if this is the equation, how can we solve the problem? We can first of all eliminate this value 5 from both of the sides. Then you can see both of the sides. Then we do end up with 2x equal 20, and we do divide 2 from both of the sides. We do end up with 10, and we can verify that 2 into 10 plus 5 is actually 20 plus 5 is 25. Great, isn't it? So why is this a linear equation? The reason is this: if you just plot it, if you in something called Desmos or so on, you can see 2x plus 5 gives us this line, and if you just see the point for this point, the value for this point, which is basically 10 comma 0, that means it has a value like basically in the x-axis in the 10 value, or in that it just basically collides with it. That means the value for x for this equation specifically should be 10, whatever it is, and the value for y is 0, because we actually don't have any value or any variable y here, right? That means, yeah, we don't need any value. That's why y is 0, and specifically the line is linear, right? You can see the line is linear. That's why the linear algebra comes in. Now let's just solve a problem. Okay, so assume that there is a police officer called sheriff with a speed of 180 km per hour, and a bank robber who has basically, they are both running a car, and the bank robber has like 150 km per hour car, and he has a head start of 5 minutes. That means he started 5 minutes ahead of the police officer. So let's just give it sheriff, police officer is P, bank robber is T, just to identify. Okay, let's just think this is the thief and start it, and the speed is 150 km per hour. Let's just divide it to 150 km by 60 minute. Okay, let's just make it minute, which should be 2.5 km per minute, and the police officer should have 180 by 60, right? So it should be 3 km per minute. I hope you understood the process. That is, we're just making it simpler, okay, rather than having 180, 150, making it simpler. Okay, like 2.5 km per hour minute, 3 km per minute. That's it, simple as that. So what's the goal? The goal is how long does it take the sheriff to catch the robber? So sheriff, we just think is P and this is T. Okay, now here is the thing: the thief had a head start, okay, of 5 minutes. That means this is the it took around, or we just draw it better, shouldn't be here actually, this point. Okay, so there is a difference between 5 minutes difference, right? So the thief was initially at this point and now it is here. that means the thief covered some sort of distance here. So let's just find the distance, which is, we know d equal vt, distance equal to velocity or speed multiplied by time. So the speed was 2.5 kilometer per minute, and the time is 5 minutes, which is 12.5 kilometer. This is the distance, 12.5 kilometer. Now assume that how long does it take? Okay, so assume that now they are in this stage, and like there is a stopwatch. Okay, there is a stopwatch and some sort of stopwatch, and a person is basically monitoring that, and he's saying like, okay, let's see how much time it takes to like the sheriff to reach and catch the thief. So he start counting the time, right? So we are assuming the time. How can we assume the time? Just like the equation we have mentioned earlier, a or something. Maybe this time we can think of something. Let me just remove this one and write this point, which is 12.5 kilometer. This is 12.5 kilometer for sure. Okay, now we are assuming something like t time. In t time from this point, like they are here obviously at a certain time when the police started, and in t time they're assuming that in this distance they are actually going to catch each other. Obviously the police is going to catch the thief. So the equation should be, again for the police officer, should be, as we know, d equal vt. That means the whole distance, obviously the d. So d equal vt, so the v should be what, 3 into t, right? 3 kilometer per minute into t. Okay, we are just ignoring the kilometer, obviously 3 into t. And for the thief, it should be actually, the whole t should be obviously 12.5 here, and then the speed and t, okay, which is 2.5 t. Great. Now if we just solve these equations, you can see obviously the d, both we have same distance obviously at certain point from the equation, so we can just call t 3t equal 2.5 t plus 12.5, and from here we can easily eliminate like 3 minus 2.5 t. Obviously we can just eliminate 2.5 from 5t from both of the sides. That keeps us 12.5, which is basically 2.5. okay, 0.5 t equal 12.5, and then we end up t equal 25. Okay, now you can say like or you can mention like, how is it possible, or so. Let's just see if it is true or not. If we just may use these things, okay, we are just going to plot this thing here in Desmos. Okay, d equal something, maybe should I write that? Okay, or we just give it v2, right? Okay, no problem. Let's see, d equal 3t. okay, and there should be another one which we want, d equal, geez, I believe we had 12.5 plus 2.5t. great. If I'm not wrong, this should be the equation, right? Great. Here you can see what happens from this. If you just zoom out, so you can't exactly see what's the point, or which is the point where they collided basically. So this is the point in x basically, or t is basically here. Obviously this is how I made the equation. So d is basically in the y-axis here, and t is in the x-axis. okay, so you will also see that in our side obviously. So if you just look into the plot, you can see in this point they collided, and basically that, and the point is 25 comma 75. That means 25, right? This is the time when they are supposed to collide. Okay, so if you just look into this, how can we verify that? We can easily verify by 3, like for any equation, because okay, so t is here obviously. You can also verify this by this thing. You can see in this point it is also mentioned that the y value or the distance they should cover is 75, because you can see 25 comma 75. So just let's just give it here. So what they are saying is the t, which is basically in the y-axis, should be 75 and the t should be 25. Isn't it true? Obviously it is, because if you just want to verify, you can see d equal to vt. 3 into 25 is obviously 75, right? So you can verify that. So this is how we can just easily do it from that slope. And interestingly, you can see these are basically, both of these are linear lines. The green is a linear line, the red is a linear line, and just using that we can easily find out when they are going to collide. So in real life we do solve problems with these linear lines. So in machine learning, basically we do have lots of problem like that, where we can actually solve these problems using linear algebra. There are two interesting points which you should know, and that is when we don't have any solution and when we do have infinite solutions. I will just try to make sure like you understand what's happening. So if we just look here again, this is exactly the same thing. Obviously you can see it's exactly the same thing. Now you may say like, okay brother, what happened here? Here you can see this is minus 5 obviously, 12.5 plus 2.5t, and here it is like 0. That means there is a difference of 5. So this is basically nothing. It basically depends, these graphs are different because they are assumed like one starts from 0, one starts from 5. Obviously this is because of the equation. We could have changed the equation, we could have changed or we could have thought about the time from these in different manner, because here it was like d equal to 3t, right? Obviously, and we had here 12.5 plus 2.5t and so on, right? But the equation could have been different depending on, it could have been we could have write it like d equal to 3t minus 5, and we could have write t equal to 2.5t. These are exactly the same, and if we write this thing, we would get this thing. So this is not a big issue. The important factor is we do have the difference of 5 and so. Okay, let's just forget about it. Okay, so what are we going to think about this thing? Okay, let's just think about this scenario. Assuming we have we just had this thing, right? The slope, just ignore 0 and 5 for this example. Okay, we have a distance between of 5, obviously the time 5 minutes, and the line for this or for the police officer was like maybe sorry, it's the thief is 2.5. we have the slope of 2.5 for sure, and for the line which has a slope for is basically 3. This is the police officer's slope. These slopes are basically the equation. Now you can say, well, what is this slope? Basically, what is slope? Let me just write the equation y equal mx. Okay, if you know about this equation, y equal mx, m is the slope, okay, and y equal mx, right? So if you just look into these equations, okay, if you just look into these equations, you can easily understand d equal vt. T is represented in the x-axis, y is d is represented in y-axis. So that means v, the value for v should be the slope. That is exactly what happened here. So we have seen it earlier as well. The v velocity or the value or speed for the thief is 2.5. That's why it's 2.5. For the police officer is 3, and that's why it's 3. That is it, nothing else. You just don't need to think about much more about it. So from these equations you can easily see that these slopes at a certain time they do actually collide with each other, this point. Okay, no problem with that. Okay, so but if the scenario would have been different, like if this is the thing, if they would have the same speed resulting in the same slope, then they would have never catch each other. And it is logical, right? Because you can see from this example, that is, this police officer had a speed of like 3 km per minute and it was like 2.5 minutes. That means the thief had less speed at a certain point. It was supposed to, like, they were supposed to catch each other. But if they continuously maintain the same speed, obviously the thief will have a head start. Okay, the thief will be ahead of the police all the time, and that's the thing. And we can also see that by the equations as well. Okay, so if we talk about our equations, if we had this equation, just let's solve the equation. Okay, so we had two equations. We had, like, this is 1 and this is 2, right? So what is meant is, what we have written is, if the slopes are same, that means if we have the same speed, that means just write d equal 3t, right? And assuming we have 12.5 plus 3t. Okay, this is the change we have made. That means that if the thief has exactly the same speed as the police officer, now what should be here? What will happen here? What will happen is, we're just going to write 3t equal 3t plus 12.5. That means we will have something like, if we just eliminate 3t from both of the side, we have 0 equal 12.5, which makes no sense. It's not possible. So we don't have any solution. Okay, that's the case 2. This is our case 2. So we have just written for the case 2. And let's think about the case 3. So for the case 3, if the slopes are same, that means if the speeds are same, but there is no head start, that means they exactly start at the same point. That means you can understand that it means that they are starting together. Okay, these both of the person, they are starting together and they're supposed to reach at a point. Now you can see exactly. Now I can say, like, okay, any time in any second they are going to catch each other. Okay, that is the thing. So they can catch, obviously they're in the same line, they can catch at this point, they can catch at this point, they can catch at this point, they can catch at this point. So every point is a solution basically. So there is infinite solution if there was no head start. Okay, so we can just visualize them in our graph as well. If we just, or the plot as well, if you just go here, 3D. So if you just, first of all, here we have head start but the same speed. So you can see, if you just remove or zoom out, you can see every time there is no collision. They do maintain some sort of distance. Okay, wherever we go. So that's the thing. But if again we do remove this one, you can see there is basically one line, because actually they are the same, right? Isn't it? They are the same. So basically you can call, like, obviously two equations colliding with each other, something like that. Every point in this line is a solution now. So this is how the things do work. Okay, we are just trying to use some basic knowledge, obviously common sense, at the same time the mathematical equations. So I do know for some folks it's going to be overwhelming, maybe especially for the students, for school students and so on. Feel free to ask our TAs in the Discord channel, like, hey, can you please help us on this problem? Can you explain it more? So we will be there to help you on this. Okay, great. Let's now talk about this equation. Okay, so before this thing, just keep it in mind, that is, in linear algebra we have just 3 solutions. We can either have only one solution, like I means 3 solution, that means 3 kind of solution we do have. First of all, we can have just one solution, we can just have no solution, we can have infinite solutions, nothing more than that, and that's good for us. So the three scenarios, we just need to keep it in mind. Now in real life machine learning, this problem is very much common, and that is we want to find out like some sort of a house price. Okay, now let me just give you the example. So assume that there is a house, okay, and you want to buy a house, okay, or one or so, okay, maybe there are two, let me just, and you want to compare the prices. Now the price for the house depends on multiple factors. One of the factors are the distance from school. Maybe there is a school, okay, this is school and this is obviously house, these are the red houses. Distance from the school, one okay, one is like maybe 2 kilometer and one is 7 kilometer, okay, and there's like number of bedrooms, okay, so this house might have 3 bedrooms and these have maybe 2 bedrooms, okay. Now and there might be other factors, maybe the history, or maybe the land, the price of the land, or maybe there is a road alongside these house, there is no road alongside this house. This can happen, there is a road alongside this house, there is no road, this kind of things. So if we assign them some sort of value and multiply with some variables and so on, we can actually predict the house price. In this obviously this session I'm not going to show you that thing, but I'm just giving you some real life use cases like how we do that. So just like the earlier thing, just like the earlier problem, we have some sort of linear algebra where y is the house price, and then let me just use this one, house price, and a is basically some sort of constant value which is y-intercept. In linear algebra we call it mx plus c. If this is the ideal equation for linear algebra, linear equation, mx plus c, this basically looks like that, like this. So this is the value for c, and this is here the slope is m, okay. I do believe you might not be able to see it properly, but let me just draw it again. Okay, let's just assume that, okay, no issues. This is going to be curvy sometimes from obviously mistake from my end, but yeah, and the value from, okay, this is the line, okay, this is the line, this is our line, okay. In the y-axis, assuming this is the y-axis, in the y-axis in this point it collides, okay. So this point, the value from here to here is c, and the slope of this line is m. So if we do, and this is the x-axis, if we go for that, this is the equation for our linear equation. This should be the image, okay, or graph. Now this is what it is. We say y equal a, this is some sort of y-intercept. So there can be a lot of things. This is not something you have to memorize and so on. I'm just going to show, or I'm just going to mention, just this kind of equations will come in, and in later on when we are actually going to solve the problem on linear regression, we are going to talk about linear regression, okay, just giving you a heads up. And maybe there is some sort of f, which is maybe distance to school, okay, like 2 kilometers. I mean, it varies, right? When we have multiple homes, we'll have multiple things, right? And the x or whatever it is, maybe lambda, whatever, you can put it or assign it here. It can be maybe number of bedrooms, and there can be lots of other factors, and maybe m is like there could be m features, much more features, and so on. Like distance from school, bedrooms, there can be a lot of other features, as I mentioned, like road and so on. Depending on that, this will be an equation, okay. Depending on that, this is an equation, just like this. We had 2 into something, a was basically the value we want to look for, just like that we have this thing. So in the machine learning process, what we will do then is we'll just add up a lot of things. Like for any house, maybe we want to know or we have thousands of houses, and we will then create equations for all of them, like the factors and the house price. Then if someone comes up and says, hey, just do let me know the price of this house, then we will just analyze from these prices, like this should be the price for this house. So okay, this is how things should work. So this kind of things we'll learn about matrices and so on in the later on. So we'll know for any house I, okay, in the data set yi should be the price, and xi comma 1 I comma m are its features, and we solve the parameter this is this. So these are the things we'll learn later on, but let's just keep it for a while. Let me just go to the end of the slide just for a moment, so that we can now talk about some solutions, linear algebra. Okay, and I believe this is important exercise. Okay. Okay, great. So yeah, we are we have done enough for the linear equations. So this is your exam, like practice. This is for your practice. Assume that we have y equal 3x and you have minus 5x plus 2y equal 2. Then just let us know about the value for x and y. Okay, so how can you solve this problem? There is something called actually substitution. Okay, if we just zoom in a bit, this is how we can solve this problem. So we have y equal 3x, right, and we have minus 5x plus 2y equal 2. Great. So how can you do that is basically you can see y have the value is basically for y equal 3x. So in minus 5x plus 2y equal 2, we can just replace this value. We can just use this equation 1 is 2 into we first write this equation, and then we just use the value for 1. From 1 we got this one from 1, so we just replace here and we do get x equal 2. That's it. If you get x equal 2, we can get from here y equal to 3 into 2, which is 6. Great, that is the solution. And what we can do is we can also plot this thing in our in the Desmos, no problem. Now this is your exercise, so feel free to actually solve these problems. X plus y equals 6 and 2x plus 3y equals 16, minus x plus 4y equals 0, 2x minus 5y equals minus 6, y plus 4x plus 1 and minus 4x plus y equal 2. So do solve the problems and do let us know like what's the solution in the comment section of this video. Okay, and that's good. And if you have any questions, feel free to ask them in the Discord server. Now let's talk about another method, which is basically by the elimination. So how can we do this process, or what is the process solving this problem? This is very easy. How is it easy? 2x minus 3y equal 15. We have 4x plus 10y equal 14. So what we can do is by multiplying the first equation by minus 2 and adding the equation. So what is it saying? That is, you can see we have 2x, right, and we have 4x, right. Now the goal is to actually now you see what happens if you just multiply in both of the sides. Obviously multiply by 2 to 2. What do we have? We have 4x minus 6y equal 30, right? Let's just forget this one. Now if you see that we have done that, obviously that's good. If we now eliminate like this was equation 2, eliminate from 2, like, okay, so we have 4x plus 10 equal to 14, and we are just writing minus 4x minus obviously 6y and then minus 30, which gives us obviously this 0 and 16y equal 6, obviously 16 minus, that means y should be -1. Okay, if y is -1, then we can easily get the value for the x, which should be 2 into x minus 3 minus 1 equal 15, which should be 3. This is 3, 15, 12. X should be 6 if I'm not wrong. Okay, let's just verify this answer by doing what? We can just verify by plotting it. 2x minus 3 equal 15. Okay, 2x minus 3y, not sure this is okay. 2x minus 3y, right, isn't it? Yes, 4x plus 10y. 4x plus 10y equal what? 10 and 14, right? Yeah, there's some great. I'm not sure if the equations are right. I will verify it again, no problem with that. You can see 6 comma -1, that means the value for x should be 6, value for the for y should be -1. Is this what we got? 6 minus 1. Yes, that is it. So we have solved the problem properly. So this is again, these are again some sort of problems which you should practice. So feel free to pause this video and practice these problems, okay, and verify if you are doing it right. And again, as we have gone through these problems and we have tried the plotting, okay, you can just manually pause this video, try these equations, solve this problem, and then feel free to try them in the plot. Okay, you can see exactly in this point they are going to collide, and that is the point where the solution is. Okay, now let's start again. We have talked enough about these things. Now let's talk about some applications in machine learning, specifically in CNN, okay, convolutional neural network and so on. We deal with images, pixels and so on. So in this video you will also learn about that thing when we are going to talk about especially the tensors. We're going to talk about that. You will see how these things like data sets are used. Okay, but first of all, let's talk about this thing. In real life, this is how things do happen. Assuming there are like 784 values, these are like used as an input, and there are some sort of neurons, weights. Basically a neural network, there are some sort of things called weights, there are some things called bias. These are used. Okay, so you can see for this image, for the input we had like a 784 values from 0 to 784, but when it passed through weights and so on, okay, it is now 784 into 64. Okay, this is some sort of matrices. Okay, matrix. Now you can see it starts from 0 to 783 and it starts from 0 to 63. So these two multiply, and that happens, and a lot of things that happens, a lot of calculation that do happen. There are also biases, which has the value for 64 as the total from 1 to 63. So that is passed, and after a while we do get some sort of output, which is from like 10 outputs, 10 lines. This is y and this is x. A lot of things that happens, we'll learn about it gradually, but these are some sort of two GitHub links you can look into, specifically like created by John Cron. So deep neural network in Tensorflow. So if you just look into that using the MNIST dataset, so using the MNIST dataset, you can see there are 784 inputs. So that is what we did see, 784, great. And then the dense layers, 64, 64, 64, and then there are like 10 classes out there. So 10 classes, obviously you will learn about this gradually. 10 classes are assumed as maybe 10 numbers. You can just look into that. And dense are the dense layers. These are the neural networks dense layers. Okay, you will know about this later on. We are not bothered about the architecture, about the machine learning architecture we're just bothered about the values. You can see weights, biases, these are passed through, and gradually we do get some sort of values. Okay, again we can also look for much more dimensional images and data. You can look into here. For example, if we had input of 74, and then we have convolution layers and the size of that second convolution layer, max pooling, dense layer, so it is much more we have much more dimensions, much more layers and so on, right? Again, this is the same thing. You can see after each thing we have some sort of taste and so on. So I do believe these are the things which are going to be much more overwhelming for you. I'm just going to share the links in the comments, obviously in the description, and you can just check them out. If you are already aware of the neural networks, you will easily understand this process, but we will learn obviously these things later on when we talk about the neural networks. Okay, so just to give you the overview, this is how things are going to help, or things are going to work. Okay, so don't worry about these things. We'll learn about this later on. So talking about these things, what are the application for the linear algebra as a whole? Is for the solving for unknowns in machine learning algorithms, reducing dimensionality, and PCA is one of the things. We'll learn about it later on. Ranking results with eigenvector, we'll learn about this thing later on. Recommenders, especially talking about the recommendations, so on. SVD is also used singular value decomposition, and especially when I was using my quantum machine learning models, I did use SVD there as well, so you'll learn about it, and natural language process specifically. Okay, just that was overwhelming for all of us, I believe. Now this is a problem for you. Kindly feel free to pause this video and solve this equation. This is exactly the same thing. If you just know the basic physics law, this will be some equations and you will just solve it out just like the linear equation we do have earlier. Now let's go for the next important thing, which is tensors. This is one of the most important part we need to know. Tensors, you see in for the Google actually have some machine learning languages, basically the Tensorflow. So the name is actually included, the tensor is included in the name, right? So what is the tensor? So tensors are basically machine learning generalizations of vectors and matrices to any number of dimensions. That's interesting. Now let's understand it much more with examples. So if we have some value, for example 5, this is something called a scalar value. Okay, a scalar value, nothing else. If we have something like 3,3, assuming 3,3, no problem with that, is basically a vector. Okay, a vector of length 2. Now you can say like, okay, what are we representing with this 3,3? It can be something like in y and x axis. In x axis maybe in 3 value, in y axis in 3 value. Here there is, assume there is a vector, and the what we are meaning is in the x-axis we have to go 3, and then we have to go up 3 in towards the y-axis, and we'll get the position of the vector. That is it, that's it. So this is basically a vector. Okay, this is okay. Again we have something called matrix. Okay, so this is something sort of matrix. We'll know about it later on gradually. This is matrix is one of the most important things you will know, because metric multiplication and so on. We'll see about it. And there is another thing called tensors. Okay, so tensors is much more. You can see there is some sort of common factors in all of them. You see this is only a value, but in vector the value is not the only thing. We have much more value, and it is there is obviously it is not only meaning some sort of scalar is basically, okay, let me just give it the example between scalar and vector. For 5, what do we understand by 5? we do understand maybe like that. That is, in this is a x-axis, and these is 5. So in a particular axis, so in a particular axis, when especially the x, where we, like for example, the thief started running and it reached 5 kilometer. That's it. So this 5 is basically the only this is a value, right? 5 kilometers is just a value. That's it. So this is basically scalar value. There's nothing with it. But if we want to know much more about it, like for example, assume that this thief actually started from this point and he started running here in this distance. Now to know, like, if the thief, where is the thief right now, right? So maybe these are some sort of our axis, x and y. So a person who is watching from here, he will say like, hey, just move like 3 kilometer from here and then go 3 kilometer from here. Although it doesn't look 3, I just added much more, but yeah, 3. Then this is the point where the thief is. That's it. So this is basically represented here. That's it. So it's basically representing the data. There are different ways to represent that. It's basically in x and y, comparing in x comma y, we're just saying like, okay, the value for the x is 3 and the value for the y is 3 as well. It can be different for sure. Now for the matrix is different. It has much more data than that, and each time whatever we say, like specifically for this vector we had the value 3 3, right? But if we talk about matrix, it can be different. It can be, we can have much more data, 3 5 3, like 3 comma 3 comma 1, no problem with that. This is a lot of things that can happen. So this is a matrix, a collection of data. But you can see one important factor, that is this unit or a specific data. This is what it is for scalar, but here we have obviously specific scalar data, and we just don't have one data, we have much more. But specifically talking about in matrix, you can see there were 2, right? We can obviously write this matrix like this, only 2, no problem with that. I'm just trying to give you a concept, that is, okay, here you can see 3 3 was a vector, but in matrix, one of the rows, these are the row, this is basically a row, the whole thing is a row, this is row. So this is row 1, this is row 2. The row 2 consists of this vector. That means each time we are basically adding our, we have much more than the earlier one, right? This is this scalar value, but this vector has 2 scalar values and it is called a vector, and this matrix has basically a vector here within it. Okay, you can just call it. So you can understand, like, okay, we're just adding or we are making it much more complex. That's it. Now why these concepts are coming up. So now if we just look into here, scalar has dimension 0, there is no dimension. For the vector we do have dimension which is 1, and basically array vectors are some sort of arrays. For the matrix we do in general have dimensions 2. For 3 tensors we do have dimension 3, and for n tensors we have n. So there are a lot of things, a lot of examples we can come up with. Okay, specifically talking about this thing into this linear algebra, we'll follow this one, and we'll also share the link for these specific one. Okay, and we'll talk about this thing later on. But if you just start, or if you just open it in GitHub, or maybe download it in your local system, you'll see earlier we did mention about the equations. You can see I did mention, like for the plot they took this equation, but we obviously had a different equation, right? This is basically the equation for the thief and the police, right? We had d equal 3t and maybe d equal 12.5 plus 3t, sorry, 2.5t, something like that. Okay, but here it's different because obviously depends. I did show you like why it's different. That's not a big issue. And yeah, this is how we can plot this out. We'll see. We'll talk about scalars and all. You can see scalars in base Python, and so we'll talk about it later on. Okay, let me just talk about the vectors, vector transposition, and then we'll talk about the code. Okay, I will talk about how to code them out. Okay, so now as I mentioned of the vectors are basically one-dimensional array of numbers. So vectors are one-dimensional array of numbers. Now what are, well, now you can say like how it is one-dimensional, as we are talking about we have x, we have y, right? Something like that. But in general, whatever you say, the vector, the one-dimensional array of numbers, is basically some sort of like x and y, right? What we do is we do represent the vector as a value, right? Maybe 3 4 or whatever. So 3 4, so it's basically one dimensional and array of numbers. So basically an array, we have some numbers in it. Now this vector can be in different shapes and all. That is what is important out here. Okay, let's talk about this. Okay, vector of length 2 represents location in a 2D matrix. Interesting point. So what it is? Vector of length 2. Okay, so assuming 12 4. Okay, this axis can be x1 and this can be x2 or y, whatever you call it, there's no problem. Assume in this certain point, like this is a vector, in certain point the value for this is, so it should be 12 comma 4, something like that, obviously. So we can represent it like this, x1 comma or x1 x2 12 4. Okay, in x1 axis it went 12 unit, and in y2 unit it went for 4 units. Okay, 12 4. So this is basically a vector. But now interesting point you have to understand, that is this is a vector and it has length 1 2 2 values, that's it, length 2. It basically represents a location in 2D matrix. Okay, that means in a 2D matrix, this is something like a 2D matrix. Okay, this is vector, but in a 2D matrix, as I mentioned earlier, matrices are much more bigger than the vectors. So you can see in 2D matrix we have we can call you have two vectors which had 1 2 12 4. So this 12 4 is a part of this 12 4, basically a vector is basically part of this 2D matrix, or showing some sort of location or value here. That is it. A length of 3 represents the location in 3D cube, just like that. Length of 3, when we have something like 12 3 4, that means when we have a huge 3D cube, 3D, assuming we have 3-dimensional thing stuff, in 3-dimensional stuff there is some sort of value, 12 3 4, it is one of the values out there, just like that. So this might be overwhelming, but the point is, let me just make it clear, that is, it's not going to be that much important for you to understand. You will just understand it later on, but it is just to give you some idea, that is these small units are one like part of the bigger units. That's it, simple as that. There's nothing you need to keep it in mind that much more. We will just learn this later on. Okay, again, important factor, that is we just learned, right? The vector can be maybe like 1 2, this is the length, this is we have length 2, okay, and when do have 1 2 3, what do we have, length 3, so something like that. So 1 2 3 4, we have 4 values, that means the length should be 4, something like that. So earlier we just knew that, came to know, that is sorry for that. Okay, the vector of length 2 basically is represents a location in 2D matrix, represents a location or some value in the 2D matrix. Length of 3 represents location 3D, length of n represents location n dimensional tensor. That means just like that. So this represents a location or value in 2D or matrix, and this represents a location in a 3D cube. This represents a location in n dimensional tensor. Okay, so this is it to know. That means These are the values that are part of that big values or big units. Okay, so just don't bother much more about it. Okay, I will learn it later on about and be clear about it. But let's proceed with this one. Here is the, as I mentioned, these are all vectors obviously, and the length varies. Okay, that is the point, the length varies. Now there are few interesting features of the vectors. What is, we can transpose them. That means we can just like for example we have a row matrix or row vector, sorry, I mistakenly mentioned the matrix, it is row vector. It's just like that, 1 2 3, this is a vector, right? So we can transpose that so that this whole thing is in a row and it becomes column. You can see how it became this like that. For example, if we have 1 comma 2 comma 3, this is a row. Okay, this is a row actually vector, and our goal is to like from row we want to make it from row to column. Okay, like you see this one is here, it will come here. Okay, the goal is to keep it in in 90 degree, you can call it, just like that, just doing the reverse one. You had, it was in the whole thing was in row, we can just take the whole thing and take it in the column. That's it, transpose the thing. Okay, just reverse it. So it was in row, once we reverse it, it became, the whole data came in a column. So you can see it is basically a row. In a row we have 1 2 3, and now in a column we have 1 2 3. That's it, nothing else. Now this is basically transposition, a lot of features and so on. I do believe you will have lots of confusions, I do understand that, but that's one of the reasons you have to learn these things deeply enough. But I'm just going to give you some overview so that you do learn, or you can start learning. Again, interesting factor, before we go for the code and we do learn about how do we represent them, the code, let me just give you the one of the important example, that is 25 comma 22 comma 5. So just do let me know if this is a vector or not. Pause this and do let me know, like, okay, yes, 25 comma 2.5 2 comma 5 is a vector or not. Okay, you can easily see from here it's a simple vector. Obviously if you just read this slide or read this note, you can understand that. But interesting factor is, you have to understand what's happening. This is a simple vector which has length 3. Length 3, that means 3 values, no problem. That is, if when we are going to use the coding, is in our code, there is something called shape. This shape basically gives us the idea about this thing. When it is a simple vector, if we want to know the shape, it will give a return us something like 3 comma nothing, then this thing. Okay, so it means we just have 3 values, that's it, and that is it. We have length 3 and that is what we were required. But if we have something like we are using 2 here parentheses, and what we do is we do get is and we do write 25 comma 2 comma 5. This is a different thing. In coding, this totally means a different thing. When we write this thing, it assumes it as a matrix. In matrix, what happens is, what is a feature in matrix? In matrix, what happens is we do have row and column. Okay, we can have multiple rows, multiple column. Row 1, assume that is row 2 and is row 3. Maybe 1 2 3 4 5 6 7 8 9. So 1 2 3 is row 1, 4 5 6 is row 2, R3 is 7 8 9, row 3. Again 1 4 7 is column 1, 4 5 8 is column 2, 3 6 9 is column 3. So in matrix we do represent rows and column or values. Now why are we doing that? Because assume that this is 5. Now someone came up and asked me, hey, where is 5 located at? I will say, okay, the 5 is located basically in row 2 column 2, in row 2 column 2. So it's easy to understand where it is, right? That is what it is. In coding, we'll use these things to make the code, make it understand, like, hey, this is a matrix. So when we input, like you see, we did input exactly this thing and we got the shape 3, only 3, that means the length. But when we add one more parenthesis, what happens is we'll get shape as 1 comma 3, which means we have row 1 column 3. And now the visualization should be like that, 25 comma 2 comma 5, but it is assuming this is row 1, we have column 3. So this is how we will instruct the code. That is important because there are slight different things which we change and the code starts understanding different things. Again, if we had one more parenthesis, what happens? It starts thinking that there is a the shape is 1 comma 1.3, 1 comma 1 comma 3. This one means that like there is some, assume that the whole plane, or there is a page, whole page. In the page there is a one row, and in that one row there are 3 columns. That's it. Okay, so it is getting complicated, right? Okay, let's get back to the code and let's just see what happens, how we deal with these problems. Okay, so first of all, as I mentioned earlier, that is we'll share this one with you guys in the comment section, in the description section. So you will just see this is the problem for the thief and the police officer. So this is how we can solve this. We could solve this out. Again, this should be your task. That is, I showed you another equation. Just download it and change this value. Okay, change these equations and then check the plot if that is exactly how I showed you the equation or not. I've just I've removed those though by now, but yeah, just ignore that. Yeah, you can just do that. You can see again in the position, you will just get the value. Okay, that's interesting. Okay, so what are we looking into? Okay, scalars and so on. Okay, so as mentioned, you can just check this out, but here is an important factor, that is when we use this one, you can see the value is 30 out here. Okay, and the difference is simple. That is, if you just look into the plot, you see it start from 0, okay, and then from 0 to 30, right? But when I showed you like the plot, it started from -5 and this was in 0. That means actually these are exactly the same, because it started like +5 from here, there were -5. So if you just add this up, it is 30. That's it. That's exactly the same value. So you just don't need to bother about it. This is how we can just do it. It totally depends on the reference. That's it. Okay, so now let's bother about the scalar and others. So you can see, as I mentioned, scalars are basically some sort of just the value. That's it, 25. If you just write x equal 25 in a Jupyter notebook, okay, you can just create this one, or I will provide this one. You will just run this out. That's it, x equal 25, and then check out the value. It is 25, no problem. Then you can write something called type x. That means what is the type? Now a variable can have multiple type, like string, then integer, and boolean, and so on. Okay, this means here the result is integer, int. That means integer. That means it is some sort of integer value. Okay, if we would have used like 25, at least like that, 25, this and this, you can see now it's float. Okay, after 25, if we do have some sort of decimal points, we do consider these as floats. Okay, that is, so this is something you need to understand. So let me just clear this again. Let me just go here and let me just write it here. So how do the, like, if integer 25 is some sort of integer, when we do add like 25.0, 25, 0.2, whatever it is, these are floats. Okay, we have decimal point, and booleans are basically like true, false. These are the things called boolean and so on. Okay, these are the things we can use. Okay, so great. So the value for this was, the type of the x is basically integer. By default it is integer. Okay, we didn't set it. It is by default. It just started understanding, because you can see it is 25, and yeah, it can see like, okay, it's 25. So yeah, this is it could understand it is integer. Now talking about y equal to 3, that means same. Now what we can do, x is 25, y is 3, we can just sum them up. We can just add up py underscore sum equal x plus y. That means we're saying x is 25, y is 3, add them both, and then pass this result to py underscore sum, and then print the result for the py underscore sum, and we get 28. 25 plus 3 is 28, right? This is exactly what happened here. Again, as we have added both integers, the result is going to be integer as well. So 28 is integer, and we can see the type is integer as well. And then different thing, as I mentioned, we could have use a float value. Now here you can see x float. We have just created a different variable called x float, and we have provided 25.0, and if we add them up, if we add float with an integer, the output should be a float. Okay, and you can see 25.0, and y is only 3 integer. 25.0 or 0 plus 3 is 28.0. Okay, now the thing is the type is float. Okay, great. So this is the thing. We can just see, we have just seen it in normal stuff. Now normally we have just seen it normally. Now if we use PyTorch is made by Facebook, and Tensorflow is made by Google team. And if we want to see the things, these things, the scalars in PyTorch and so on, you can just do that, no problem with that. So what you have to do, first of all, import torch. We have to install torch. Okay, by default it's done here, so you don't need to do it. So what you have to do, then once you're done, you can just write like x underscore pt. Pt is for PyTorch, that's it. Just to, it's totally up to you, whatever you want to write. Then you have to write torch dot tensor, because now, as I mentioned, tensors and important factors, anything in the mathematics are basically tensors for us. If we have just one specific value, it is just a scalar value, that's it. Okay, so we have to write torch dot tensor, then maybe array or whatever it is, vectors and so on. So here we're just providing the value. That means when we just provide a single value, it is scalar, right? Okay, then we just print this out, x underscore pt, which shows tensor bracket 25. That is it, and we can again check the shape of it. Okay, interestingly, I have mentioned the shape of other stuffs, right? Like shape of this, but I haven't mentioned this is a vector. We'll see, obviously we'll learn about it, how to do it, how to find the shape, but I haven't mentioned the shape of this one, this thing. X is scalar value. Basically shape is actually these things. So for the scalar we have 0 dimension, that's it. So the shape is going to be 0. There's not going to be anything, so it's going to be 0. That's it. So you can see there's nothing. That it means is, okay, there are no dimensions to report. That's it. Okay, great. Then interestingly, what can we see now? As I mentioned, if you just provide like one parenthesis, so what we can see, 25, right? You can write 4 for sure, no problem with that, whatever you write. Now you can see the torch size is changing, right? Interestingly. So what is it? What are the things we're learning, right? So as I mentioned, like from here, whatever. Okay, here you can see xy, we represent it by 3 3, right? Isn't it? So 3 3 had basically what in general, what did we have? We had a 2 dimension, right? X y, in x axis we had value 3, in y axis we have value 3, so that's why it was 3 3. That's what we have inputted, right? So for here it is 25 4, no problem, just like that. So it has 2 dimensions, x y, just like that. But if we just have this thing, only one. So if we have that, vector obviously can have length 1, vector can have length 2, vector can have length 3, whatever, right? So if we just have this thing like 25, what does it mean? It means the x-axis we have 25, okay, and meaning you have x-axis. Okay, but when talking about scalar, we're not considering the axis. We're basically considering that it's simply a value. That's it. There's nothing, no dimension with it. You don't need to bother about dimension for the scalars, but here we just exactly had some sort of value here, but it was considered as scalar and no dimension was here. But if you just add parenthesis, is assuming okay, we have some sort of axis here. That's it. That's why we are getting 1. Now here we are getting 2. Sorry, not 2. Here we are getting 1 comma 1. What does it mean? This 1 comma 1 means some important factor. Let me show you. So as I mentioned later on, just look into here. Where was that? Here you see 25 comma 2 5. Here you see we had 2 parentheses, right? What it understand is there is a row and there are 3 columns. That's why it is 1 row 3 column. But in our example, what we have used right now is 25. That means if we consider it row and column, we have just 1 row 1 column, right? Isn't it? You can see 1 row 1 column. That's it. So these are the things. You will get this code. I will share that with you, but you have to understand what is happening, why this output is here, what does it mean. That's it. Because nowadays AI can generate these codes, but to understand what's happening is much more important. That's many people don't understand. Okay. Now scalars we can present scalars obviously in Tensorflow as well. We just have to download Tensorflow and import Tensorflow as TF, and then you can see how can you do that. X underscore TF Tensorflow, and we have to present by TF dot variable, then 25, then comma, and the type of the thing. So it's by default is set as an integer, so you can ignore this one, but yeah, this is how you should actually assign some sort of scalar value here. So here you can see it's just 25. Okay, so if you just look into that, you will see variable shape is nothing, right? That means it is assuming this as a scalar, because scalar has no dimension, right? The value is 25. And you can see something like Numpy. Numpy is basically which we use for mathematical calculation. Numpy. Okay, so especially PyTorch and Numpy, sorry, PyTorch and Tensor both actually calculate stops and are like we do actually calculate, or we do write codes basically Numpys and so on, and then we do use the Tensorflow as well. So they both are dependent and they both should be able to contact each other. So you can see easily we're just using the Tensorflow, and this is scalar value, and it's again saying that the Numpy value, that means Numpy is basically for the as I mentioned the values or in coding, basically we use Numpy to calculate or do the mathematical stuff. So it's just getting the value, that's it. So the value is 25, that's it. The shape is nothing here, that is important. Again, you can just find it out from here as well. X underscore TF shape is nothing here. That means it is understanding it as a, or assuming it a scalar, that's it. Same, so two scalars again YTF, then we are assigning it 3, and then we can just add them up. We can just see, and we can see the summations actually shape. So you can see again there are no shapes. Okay, great. Okay, great. The sum is basically TF underscore sum. So the value for it was 3, it is 25. So when we add this up, and TF underscore sum should be 28, right? So you can see the value is 28, right? Again, we can specifically find out the Numpy value by using TF underscore sum dot Numpy and this function, and we can just easily see the value is 28 and saying np dot integer 16. That means 28 is an integer and Numpy is used and so on. Okay, great, nothing to know much more. Okay, vectors, interesting. So vectors, as mentioned, this is a vector of length 3. Okay, so in Numpy, using this is basically using Numpy. Okay, as I mentioned, we can do mathematical calculations and other using Numpy. So np.array, so you can just write this thing, 225 comma 2 comma 5, no problem. So you can just print the x. So you can see this is an array, basically Numpy array. You can see the length of this thing, len and bracket x. You can see the length 3, that means we have 3 values. You can see the shape, you can see 3 comma. Okay, what does it mean? As I mentioned earlier, you can see, if you just see 3 comma, that means we have 3 values. That's it, nothing more. Okay, I mentioned this earlier, right? Okay, if you just check the type of it, you'll just see this as n-dimensional array, nothing more. As basically n-dimensional multi-dimensional array. Now you can say why multi-dimensional, because you easily understand, like here the values might represent x, y, z, maybe because we previously had for this, we previously had for x, y we had 3 3. So maybe for this we have for what like 25 2 5, right? Maybe for x, y, z, no problem, multiple dimension, we can have multiple dimensions in this array. So yeah, no problem with that. Okay, you can also find the values from the array, like 25, there is something called index. In coding we do start with 0 index, that means 25 has some index called 0, it is 1 and 2. So that means if you want to find the value for if you want to find 25, what we have to do is x has the value 25 comma 2 4 5. So what we have to do is we have to do this x parenthesis 0, that means we just want to find the first value which has 0 index. That means first value has actually the 0 index, which is 25. So these are the things, these are the basic things. I believe if you know coding, basic coding, you know about it, but if you don't know, this might be very much overwhelming for you. But I believe you just start learning basic Python, you will just understand it properly. Okay, then we can also check the type. You can just see it's integer, that's not a different thing. Vector transposition, so we have again check the vector transposition, right? This is the vector transposition. From it, the whole thing was in a row, it was a row vector, we just converted it to column vector, that's it. And you can check the shape, what is 1 comma 3, that means row 1 column 3. You can see if you just write it, it's a row, right? And there are column 1, column 2, and this is column 3, isn't it? And talking about this thing, what is it? We have row 1, row 2, row 3, and column 1, right? So that is why we have row 3 column 1, that's it. So if you just use this thing, we can basically use in the Numpy, you can just use t. Okay, this t is to make you understand the transposition, and if you just use that, you can see it will convert from this to this. Okay, you can easily do that. Okay, from 3 to 1 comma 3, right? By shape is this. Have we used this one shape, but can transpose 3? Here is C 25 to 5. So I've just converted that. XT, not sure about XT. Did we provide XT here? I don't think so. That's why the value hasn't changed yet. You can see xt equal to x comma t. Okay, we have x. So yeah, we should be provided, right? To 25 comma 2 comma 5, right? It should be transposed. Okay, let me just run all of the stuffs. Okay, great. Okay, transfer regular 1D array has no effect. Okay, transposing a regular 1D has no effect, but this has an effect. Why is it? What is the issue? Okay, what's happening is you can see this thing here. You can understand when we are passing two parentheses, it understands that okay, we have row, we have column, great. But when we have this thing, okay, it doesn't understand by that manner. It thinks okay, it just have simple 3 values. Why are you considering it our row and others, it just have simple values. That's it. Array, whatever it is, it has simple 3 values. That's it. But when we do pass this, we pass 2, consider, okay, there is a row, there are some column. Okay, now if we use transpose, it has some sort of change. That's what happens. You can see, what did I mention? Okay, yeah, if you just say transposing a regular 1D array has no effect. That's it. That is one of the reasons. But it's basically depends on how we represent it. Now if it was your goal, like for example, when I gave this representation, or when I explain this representation, this is not how the code is. If in the code, if you just represent it like that, only the one dimension or something like that, 1D, it won't understand that there is row and column. So you have to add one more parenthesis with it. So it totally depends. Like obviously I can understand if you're confused. That is if this is basically how the mathematical thing works, but in the coding you have to be conscious about it, and you have to understand how to make the code understand that this is what you want. Okay, you also have to understand about it. Okay, obviously so this is again done. Okay, so let me show you how, when it is done, when it works. Okay, exactly here 2525, as I mentioned just earlier, that is when I want to know, or when I want to represent row and column both, I have to add 2 parentheses. Then when we do that, it understands row and column. Now if we use T, just the example I provided, row and column, we get from 1 3 to 3 1 or something like that. So 25 25 to 2 or something like that. Y, we haven't yet applied that. So it is here, it's just one here we have 1 row 3 columns, right? 1 row 3 column, no problem. When you use the transpose, we get 25 to 5. That is, you can see it's in the column, and now it changes, it's 3 row 1 column. That's it, done. Okay, again we have something called 0 vectors, which is all the value in the vector should be zeros. Okay, we can just do that. We can use these, because now you can ask, hey, where should we use that? Please keep it in mind that if in this video, if you can't see this, please kindly let me know in the comment section, because it's one of the goals to show you where we do use zeros. Okay, in the MNIST dataset we'll use, or some sort of image dataset, we want to make sure you understand like that. You will see there are lots of 0 values, so this is important, the 0 and so on, just to populate values and so on. You will see np.zeros, just to make understand, like we want to have zeros, all of the values should be 0, and we should have how many zeros? 3. That's it. In vectors in PyTorch and Tensorflow. Now interestingly, vector of 3 length, that's it. And 25 to 5, this is how we do it in PyTorch. This is how we do it Tensorflow. That's it. Now let's go for norm, a different topic. Okay, now let's talk about norms. What are norms? Basically, now let's understand what it is. So in this vector as a whole, we did know that we had to go 12 units here in x1 axis, and then 4 units here in the x2 axis. Okay, but as a whole, if we had to know what's the length of this thing, how do we know? It's simple, right? We know about it by, how can we do that? We could have just used like 12 square plus 4 square then root, right? That's it. So it's basically L2 norm. So for this example, it's different. That is for 25 to 5, assuming that we have this array, which has basically 3 dimension as a whole, a vector with 3 dimensions. So same, no problem with that. Just assume this like this. For example, this can be understood like that. Okay, so it is 25, like maybe in certain point 25, here 25, then 20, and sorry, here 2, and from here something, from here to here we have 5 or so. I just forgot about the value. What was the value? 25 to 5 or something like that. So it's in 3D, okay, in 3 dimensions. That's it. So in 2D, when we had 2 dimensions, what we did, we exactly basically squared them and added them, and just add the root square. That's it. That's what we're going to do. So if we have much more than that, we can just do that exactly. So L2 norm is basically, the goal is to, like, first of all take all of the squares and then root them up. This is how we can do it manually. Okay, you can do that manually. If you use 2 stars, it basically means 25 square. That's it, 25 2 star, and then whatever you give, maybe 3, then it will be 25 to the power 3, something like that. So it's basically the power means, okay, in Python. So simple is basically the manual way, but what I can do is, you can just use this Numpy function. As I mentioned you earlier, that is, Numpy is mostly used for the mathematical calculations. Here you can exactly see NP. NP is basically for the Numpy. What we did in our code is import Numpy as NP. That means when we mention NP, it will understand that we are using Numpy. That's it. And there's something called len alg, okay, dot norm, that x. What is the x? X is 2525. When you pass this out, we get exactly the same value. That means manually we can check this out or do that, no problem. So this is how we do the norm, okay, L2 or L3 norm. So basically it's L3 as a whole, and talking about L1, okay. So if units in this 3-dimensional vector space are meters, then the vector x has a length of, oh, okay, no problem. Now we can again talk about L1. That was, sorry, my bad, that was L2, okay. That is L1. So what is L1? When we're using L1, what we do is, we don't use squares, okay. We don't use squares, but what we do is we just add them up. That's it. So here you can see, when we had 25 to 5, what we do is we just take the whole value, 25, then 2, then 5. What do we have? 25 plus 5, 30, plus 2, 32. That's it. So that is basically L1 norm. Now you can ask, why are we learning these norms? Well, I will mention that within a while, but yeah, after that, a squared L2 norm. So squared, you can see L2 norm, we have just learned it, L2 norm. That is, we have to square all of the values within the dimension and then take the root. But when we are calling it squared, that means the root should not be there, right? If you just look into here, squared, see the norm, if we just want to represent L2 norm like this, okay, root over, and all of the values we just sum up, and obviously squared sum up. And for the squared L2, just have a square here, so the root is gone. That's it. That means squared L2 is basically the square of all of the value. That's it. So if we just go here, and if we just take this value, you can see we just take the square. That's it. So you can again do it in multiple other ways. One of the ways are basically dot product, okay. X with the x has value 25, and comma 2 comma 5, and if we just multiply, or if we just do a dot product, vector can be, we can have dot product with this, then we can easily understand the value. Simple as that. We can, so there are a lot of ways you can understand, a lot of things you need to know, but yeah, surely once you do a lot of practices, you will understand what to do. And max norm, you can get the max value. You can get the max value from here. You can see 25 to 5. If you want to, if you use the max, basically you get the max value. What is it? Which is basically 25, right? Then we have something called orthogonal vectors, okay. So we can do that as well. So what is orthogonal vectors? Okay, again, if we're talking about this, we should know about the generalized LP form. So we have just seen that earlier, just talking about just L2 norm. If you just look into L2 norm, you can see root. This root basically means we have a power of 1 by 2. That's it, which we have again used here. Where here's we have used, you can see the power of 1 by 2. That's it. So the generalized format is pretty easy. You can just understand the generalized format, and that is there, just a thing, p to the power 1 by p. That's it, simple as that. So when do we use that? We basically, you can see this p can be a real number and greater than or equal to 1, and can derive L1, L2, L infinity norm formula by substituting for p, and also norms, particularly L1, L2, used for regularized objective functions. This is what is going to be important and going to be handy later on. Okay, just keep this in mind. I know this is very much overwhelming if you're just watching it for the first time, but yeah, just hang on with me. Okay, interestingly, there's something called basis vector. So what is it? The basis vector is, if we have x-axis, if we have y-axis, so in the x-axis the value we do have maybe I, okay, and in y, now assume this is 2D, obviously 2 dimension, right? X dimension, y dimension, okay, and this is j, right? Okay, so in from 0, the first value or the first unit, obviously here is 1, right? So, and from here 0 to here is 1 as well, right? So we can present this value, this point as 1 0, and we can present this point as 0 comma 1, right? So basically these are our these two, we can write 1 0 or 0 1, or we can just present it like this, just mathematically for the coding part, like 1 0 0 comma 1. Okay, so these are basically simple vectors, but we are meaning 2 dimensions, where we just have a x-axis value here, and here we have y-axis value. Okay, no problem. These are basically basis vectors. Why? Because using that we can reach any point in that dimension. Now you can say, why, how? Now here you can see it is a 2 dimension, right? Let's say, right, let's just look for this how, why, right? Great, let's look for this. Okay, assume that our goal is to reach I don't know, it is 1.5 maybe, yeah, 1.5 I plus 2j. Okay, maybe this is our goal, something. Can we reach that using these values? Yes, we do. How? We can see that what is this 1.5? In this, let's just see this one. This is 1.5. This is 1. This is 1.5. That means in x-axis we had to go 1.5 unit. In y-axis we had to go 2 units. That's it, right? Isn't it? That means we are using these basis vectors. That means here, if we had to multiply 1 comma 0 into 1.5 plus 0 comma 1 into like 2, we would actually get exactly the thing, right? Isn't it? 15 comma 0, or which is actually basically 15, and for j we can call it, so it is I, it is j. Yeah, this is the thing. Okay, so these vectors, this is a vector, these are our basis vectors, but using them we can reach any point in this 2 dimension for sure. Obviously it is 2 dimension, and 2 dimension has these 2 basis vectors only. So these are our strength, or this is what we can use basically. So using them we can reach any point. Now we can say 100i, then 200j, whatever you call it, we will just multiply them, right? Isn't it? So we can use them. So we can use them to reach any point. So this is the power of basis vectors. This is important. But another important factor is you can see the basis vectors here do have 90° within them, right? Isn't it? You can see 90° orthogonal vectors. That means, and another interesting factor is, if two vectors are orthogonal, the dot product basically, like you can see x and y are orthogonal vectors if x transpose y equals 0. Okay, interestingly, x transpose y equals 0. That means what? That means if you have two vectors like maybe 0, like 1 0, and 0 1, okay, x is this. If we use the transpose, what do we have? 0 1 0, like this, and then 0 comma 1. Now if we multiply 0 comma 1, yes, 0, and yeah, 0, and this plus 0 comma 1, which we get is 0. So we get 0, right? But yeah, this is how we can do that. Now this is you can see it is 90° again, so it does mean the now why did I use these two? You can see ing. So here I vector is meaning this thing, this unit basis vector. It is representing this thing, and the second you can easily see the 90° between them. So this is the orthogonal vector. And how can you do that? We can easily use dot products. So when we use dot product, we can just see if we have 0, we are good to go. Now if we just come up here, orthogonal vector, you can see array 1 0, again another array 0 1. If we use the dot product ij, you can see 0. That means they are they have a 90° in between them, right? Okay, orthogonal. Great. So now these are some of the exercises you should do. The exercise are, feel free to pause this one and check this out. You can see 25 to minus 3 to 3. So I can just check this on, and using the algebraic notation, what are the dimension of this matrix, what are the dimension, and using algebraic notation, what is the position of the element in this matrix y with the value of 17. That's good. Again, tensor transposition, that's interesting. Okay, so earlier we have seen that maybe if we have some sort of scalar value, if we just transpose that, we can actually get the same thing. Basically it's common sense. That is, if we just transpose 5, we'll get 5, because there is no dimension, there's nothing. If it's just it is not reverse, doesn't mean like from 5 we will get 1 by 5. It just means like we're just changing the position from row to column, that's it. But it is it doesn't belong to any row to column, or if it belongs to one column, it is actually the same thing. So x transpose equal to basically x, and transpose of vectors seen earlier, we have seen that converts column to row, right, and row to column. So this is what it is, isn't it? Row vector, if we transpose, we get column, and if we transpose this one, we get this one, same thing. But this is not enough, there's much more than that. Now we can say, what is that? In general, the real transpose or transposition actually happens for in the matrix. Okay, the matrix is not limited to like basically the simple stuffs or maybe one row or something. Matrix have multiple vectors within it, just like that. Okay, you can see the lots of things. x1, so here 1 2 3 4 5 6, we have 6 values, right? So what happens is basically when we transpose a particular value a particular matrix, what happens is, now you can see that assume that we have in this matrix, assume that we have this value, right, x1 comma 1. What does it mean? It means the value is in row 1, this row 1 and column 1, that's it. When we use the transpose to the whole matrix, what happens is it flips. the value now goes to the reverse one. Okay, that means it should be in the column 1 row 1. Okay, so actually these are the same thing, right? That's why it is not that different. Okay, let me just give it with another example. That means we can give it this one, x2 comma 1. Okay, so it means when the transpose is applied to this value, it means the value is in row 2 column 1. Okay, you can see this is our row 1, this is our row 2, this is our row 3, this is our column 1, column 2. So it was in row 2 column 1, but when we use the transpose, it flips and it will now go to different thing. It is in row 2 now, right? Now it will go to row 2. No, it won't go for row 2. The value will go in column 2 row 1 here. Basically you see row 1, row 2, column 1, column 2, column 3. Although we have written this thing right, you can see row 2 and what is this? It is basically row 1 column 2, right? Isn't it? Actually it is written because so that you understand where this value flipped and where it went. That's it. So the thing is, it was basically in row 2 column 1, but now it will flip and go to a position. In which position? The position should be basically where the row, it is, just let me write, it is row 2 column 1, but now it will flip and it will be row 1 column 2. That's it. Okay, flips this position. Okay, flips this position. Now you see here. Okay, that's it. This is actually the this is how we should represent row and columns, but this is not how we should represent, but this is basically to show you where it flips and where it went. That's it. Okay, simple as that. Great. Now if we can understand how this thing works in matrix, basically all of other things are basically the same thing, because the tensors and others are actually the bigger version of the matrix. So yeah, now you can now this is your task, that is to understand or to give us the answer for this transpose. So here we have y equal this thing, and what is this thing. Okay, so what is the value of this? Another important thing is, what is the Hadamard product of these matrices? Now you can ask, or you can use AI to understand this thing, but let me just give you the hint. That is, Hadamard is basically meaning when we have, you can see we have row 2, right? We have row 1, row 2, column 1, column 2. So we have 2 into 2. You can call it 2 into 2. That means we have 2 row, 2 column. Exactly here we have 2 row, 2 column, 2 into 2. When we have two matrices of same size and we want to multiply them, that is basically called Hadamard product. That's it. And Hadamard product is basically is done by multiplicating through elements. That is, if I just give you some hint, and that should be, the multiplication should be 25 into minus 1, 10 into 7, minus 2 into 10, 1 into 8. Actually I didn't give you the hint, I actually mentioned you the answer. Now you can just check this out, like how the Hadamard product is done. Okay, now don't mix it with Hadamard gate and something in the quantum computing. That's totally different thing. Now okay, we have again mentioned this how to solve the linear systems here. So yeah, that's the thing. Now let's now end this session with some examples from we will check some examples here, how it is done, how few things are done in the coding, and then we will end for today. Okay, so here you can see that rank 2 tensors here, use array within nested brackets. Okay, we have just one, right? And then we have 25,2, 5,26, 3,7. So what do we mean, or what do we understand by here? What we can understand from here is, if you just check the array, it is basically we have what? We have 3 rows and 2 column. 3 rows, 2 column, and you can see 3 rows, 2 column. Okay. Okay. There is something called rank, which we haven't talked about here, but yeah, we believe to cover this in later of our sessions, or you can just check this out, what is rank and so on. Okay, so 3 2 and x comma size. If you just check the size, that means how much value we do have. 1 2 3 4 5 6, 1 2 3 4 5 6, right? 6. Okay, again from here we can specifically select some values. Here what do you mean? X, we have colon and comma 0. When we have colon, what do we understand is colon means everything. So first understand this thing. The value before this comma should be for the row, value after this should be for column. When we using colon, that means everything in the row, right? So we have everything in the row. So what do we have? So in the row, these are the rows. In the rows, what are we looking for? We are looking for the first value in the rows. In these rows, we have the first values as 25, 5 and 3. So these are the these three. So these are few things which is called slicing and so on, like just like the vector of size 3 is part of 3-dimensional cube, just like that. So it was sliced and we took the smaller value, just like that. So we can just do various things to just take specific values if we want. These are the few techniques which, if you know the basic Python, you will just understand it properly. And matrices in PyTorch, so the matrices can be represented just like that. You see, the same thing we represented earlier. We just need to mention torch.tensor, that's it for PyTorch. Okay, for TensorFlow we have to mention tf.variable, then the same thing, exactly the same thing. And we have something called rank and so on. As I mentioned, rank has not been covered here, but yeah, I believe to cover it in later sessions. But if I do miss this out, feel free to actually ask that in the comment section so that I don't miss this out. Okay, now let's talk about tensor transposition again. So the tensor transposition was basically this one. Okay, this is what we ended our session with, right? So this is the tensor transposition, because we have talked about the matrix transposition, or the matrix is basically 2-dimensional as a whole in general, x, y or something, or so, or 3-dimensional, it can happen. But tensors are much more beyond that. It can be huge. Okay, so this is the thing. So here we have x as this 25, 2, 5, 6 and 3, 7. We have just said it earlier. What you can do, we can just use the transpose. It will be applied actually. Now we can say, why is it applied? Because you see there's a difference between a few things. When I mentioned, when we use this 1-dimensional, like 25, 2, maybe 5, right? And we just pass it in our code, it just thinks it just like a vector. It doesn't have row and x, row or column. This is how the code thinks. But if we want to make it think like, okay, this has some row, like row and some column with it, we just have to add as a whole 2 parentheses as a whole. Okay, 25, 2, 5. And once if we pass this, if we want to have the transpose, we will actually get the exactly same value, because it doesn't understand that. But when we pass this, and we will get now the different thing, 25, 2, 5. Okay, right? So but same for this, like now we have passed a different thing, right? We have, if I'm not wrong, just 25 to, let me just check the value, 25 to 5, 26, 3, 7, 5, 26, 3, 7, and this were here and here. This is what we have passed through. Now it can exactly see that we have some sort of row. We have row 1, we have row 2, we have row 3, and we have column 1, we have column 2. So once we want to find the transpose, what we will get is we'll get 25, 5, 3, we'll get 2, 6, 7. Now we can say, why are we trying to look for transpose and so on? But yeah, I will talk about it. 25, 5, 3. Yeah, 267, right? Exactly. We can do this kind of stuff, a lot of things we can have, we can do that. Okay, now the thing is, why are we doing this transposition or basic actually basic stuffs? The reasons are in the machine learning algorithms we actually are going to apply these things. Okay, there are a lot of mathematical equations where is going to be applied, so that's why this transposition is going to be handy. Okay, so just learn this stuff, so it's going to be handy. Now let's talk about the basic arithmetic properties. So here you see the x, this is x, which has 3 rows, 2 columns, and value 25, 2, 3, 26, 3, 7. What we can do is we can multiply. There are few arithmetic properties we can do, like we can multiply 2 to all of the values. You can see 54, 54, every value has been multiplied by 2, everything here. We can also add 2 with every value. You can see every value has been added 2 with it. 25 plus 2 is 27, right? Again, we can do both of the stuffs. We can multiply with it and then add 2. We can do that. A lot of things we can do. These are the basic and stuffs. Here using the torch, you can again do that. Here by using the Tensorflow, you can do that. Okay, again talking about the Hadamard one, as I mentioned, the Hadamard where we have an exercise, right? So it's again mentioned here. If we have the same size, if the two tensors have the same size, operations are often done by basically default applied element wise. This is not matrix multiplication. This is basically Hadamard product or simply the element wise product. That's it. Now that's it. You can just check this out. There is nothing. These are very much redundant stuffs. Reduction is again reduction is basically the summation, because we have 25, 2, 5, 26, 3, 7, right? If you sum all of this thing, we'll have one value, and that is 68. Okay, you can see x is this, and if you just sum, it will be 68. So it is in a sense reduction, right? Because we have 1, 2, 3, 4, 5, 6 values. Now we have 1. That's reduction. That's it. You can just use a PyTorch for this. You can use reduce sum, something like some method for Tensorflow. You can use that. So this is how we can do that. Okay, there are a few other things like maximum, minimum, mean, product. You can again do that using that. Okay, finally the dot product. The dot product we have been talking. This dot product is going to be very much handy in the neural networks we are going to work with. Billions of parameters are actually calculated. Okay, so here you can see the dot product is something like x dot y, x transpose y. This is another thing which what is it? You learn about it later on, but these are the things that's going to be handy in our coding stuff. Okay, so how do we calculate the dot product? So it's basically simple. That is, if like x is an vector and y is a vector. Okay, so assume that this vector has 2 elements, the first and second. This is first and second. What we do, we basically multiply these things, like the value first element of x, the first element of y is multiplied, and then add just like that, and then we do for the rest, and then we just do add them up. That's it. And I have done that earlier for the basis vectors. Okay, we've just added like 1 0 0 1, and we've just done that, and then we've just got this one. Okay, so this is actually the same notation in quantum computing. You will see this notation is actually used to mean the actually the dot product. Okay, as a whole, you will see that, and obviously we are not going to cover this out, but yeah, x dot y is actually x transpose y. That's it, isn't it? Isn't this what we have done here? If we have x, it is x transpose, and this is y, and we have used that, and we've got 0. This is the dot product, and here is the important factor. When the dot product is 0, it is orthogonal. That's it. But the process is the same. So you can write x dot y, or call x dot y, like x dot y, okay, dot, we have to, or x transpose y, or this. Now as this is part of something which we are not going to cover, I just wanted to show you, because in quantum computing, again, this is what we do to find the similarity. Dot product means the you can see I and j are not the same, and this is what we can understand by the value 0. Now you can say how? If the dot product is 0, you can see these x's are not the same, they have so much difference. But if we do have a very good value like 1, you can say okay, they are the same. Now you can say how? Let me just do it. If we have 1 comma 0, if we just have the exactly same 1 0, right, and 1 0, okay, same value, so the transpose of this should be. Now you can again ask me, brother, you just have one parenthesis, you are saying it can be row to column and so on. There are a lot of things in coding, you have to reason it differently, but in mathematically this is how things to work. Okay, don't confuse about it, but let's just focus on it. 1 0, so it should be 1 0 to 1 0, and this should be 1 0. Right now this 1 and 1 should be multiplied, 1 into 1 plus 0 0, which ends up 1. 1 means there is you can see 1 0. What does it mean? As I mentioned earlier, 1 0 is basically the I. That means we have 2 I. That means, or maybe assume that this is some sort of m. We don't know where it is. And you see this is I and the m is actually exactly the same. That means they have so much similarity, they are actually the same. That means this is how we can find the similarity and so on. There are a lot of things. Just don't need to bother about it right now. But this similarity and others for the dot and cross, you need to know why this, why do we use dot, why do we use cross product. Okay, great. So this is actually the same way to represent dot. So we haven't talked about cross product because we don't use actually cross product here. Cross product is for the physics, to be honest. Solving linear systems, so we've just seen that. How can you do that? We've seen that how to solve the linear problem, y equal to 3x minus 5x plus 2y equal 3, 3x minus 5x. So you can just plot this in the Desmos. You can see where they collide with each other or intersection point, and you can again check this code, like how can we see this point. You can see exactly this point, 2 comma 2, the value for x and the value for y 6 2 6, isn't this the value 2 6? Yes, same for this one. You can again use some technique like multiply it by 2 or minus 2 and so on. We can do, and we will get 6 minus 1. I believe we have solved this problem earlier, if I'm not wrong. 30 16, yeah, I believe so. We have just done that earlier, but yeah, you can again check this out from here. From the plot, it's been done, as the value is, intersection point is 6. Yeah, the intersection point is maybe something like minus 1, I believe so. Yeah, this is what we have, 6 minus 1. So yeah, that should be it. We have provided multiple exercises. I have mentioned to you about some real world problems, and yeah, I've showed you some like the sheriff and the thief problem. I believe we can also solve this problem in another different way. No problem with that. 30, and it depends on the axis, and we have multiple exercises, theories and so on. If you have any questions, feel free to ask in the comment section, and I believe this should be overwhelming for some of the folks, but again, this will be much more easier once you try to cover the topics manually. Okay, you feel free to check some books and check other videos to learn these topics in depth. Okay, so thank you so much. In our next videos, we will try to cover all of the contents of the mathematical dependencies we do have for machine learning. And yeah, thank you so much for watching this video. If you do like this video, feel free to give it a like and feel free to share it with your friends and others. Okay, thank you so much, and hope to see you in the next video.